Welcome to the last lecture of this Quantum Field Theory 1 course. We are wrapping up this course by computing one scattering amplitude explicitly. It's between electron and positron, which can annihilate into pure energy. And then out of this energy, we create other particles. And just for concreteness, I'm thinking of the muon. It could be anything else. It could be a tauon, it could be quarks, and I think I'll comment at the end about the experimental significance of this, but it is also from the computational point of view, a very appropriate process because it's probably the simplest to compute. We'll have, in principle, we have to compute the time-ordered correlation functions of 4 fields, fermions, and then apply the LHZ formula, the reduction formula. But then we saw yesterday that we can shortcut this process because the differential operators in this LHZ formula eat up some propagators, those external propagators. So if I have a diagram, shall we give it away and say what the diagram here is? No. So I have external points. In this case, there are 4. Okay, so I keep the 4 points. And then I have a number of vertices from the interaction. And then say this is phi to the 4. Then I could have a diagram which looks like this. That's not this process. And so they are internal vertices, these things, which are integrated over. I like to call them Z and W. These are the locations in space-time, and then we have the external ones, x1, x2, x3, x4. And all the lines used to be propagators. These Feynman propagators, because it's a time-ordered thing. So for this, it would be a df x4 minus z. But then in this LHC formula, you act on these external points with derivative operators, depending on what kind of field. It's a little different for scalars and fermions, but the effect is the same. It just eats up this propagator. So this is gone. And what is left is just an exponential, or these spinor, Dirac spinors. And so I'm going to list the rules which give us straight the Feynman amplitudes rather than these endpoint correlation functions. So the difference is just that these external propagators are missing. So if a particle comes in, it's a scalar particle, then this is an internal one, it's labeled Z, say, and this is an open end. This is where the particle comes in, and I label these lines now with the momenta, because I'm talking about scattering amplitudes. I have to, the answer will be a function of momentum. And so I'm drawing an arrow. If it's going into the vertex, it says it's an incoming particle. So that's a scalar. Great. This is in going, and then we have out coming. That looks like this. So the arrow is away from the vertex. And here I write P, and here P, usually it's K, but it doesn't matter. And that's the vertex P and Z. And then I have to, no, the Feynman rule says, if you see this, you write an e to the minus I, this momentum times this vertex, and you're done. And if it's this thing, you write e to the I, P, Z, and you're done. So instead of this propagator, you only have this thing left, and then you write all the rest of the internal part. If it's a Dirac spinor, particle say, rather than antiparticle, This looks like this. Fermion lines have arrows because the propagator is not symmetric. Propagator. So my list, these are the external particles and here will be the internal lines. So I'll write the propagator down here, I guess. Internal lines would be propagators. And for the scalar, this y and this is d I to the 4I squared minus f squared plus epsilon and e to the minus I p is y. And this function is symmetric in the argument. So if I switch them around, replace x minus y by minus x minus y or y minus x, then it's the same. If I change it, I get a minus sign here, but I can change the integration variable from p to minus p, and the minus sign is back there, and this is quadratic, so I don't see it. So this is symmetric, so I have this is equal to y. That is not the case for the Dirac particle. Because this thing is so we need an x, a, y, and p. These are the spinor indices, d, f, a, b, y, and that's integral d4 e 4 I p sketch and a b minus m squared I also e to the minus x minus y. So this is linear in p. And so if I switch the sign, this goes away, but there I have signs. It's not the same. It's not symmetric. So then you have to know from where to where are you thinking, and for some reasons I draw the arrow this way because kind of I don't know going on the right. So if I see this arrow, I have to take the difference from here where it points to there, well, the other way around. So these fermion propagators have an orientation. Remember, this was this thing. Psi bar. So they are different fields. There's a contraction between a bar and a psi, and there's not between psi and psi. And so you see that it's not symmetric. The x and the y are different. One appears in psi and one in psi bar. So then also my external line has an orientation, and if it's going in the arrow, then it's the particle, and if it's going that way, it's the anti-particle. This is just always sign particle and anti-particle. And the exponential factor is the same. If I label this line with the p and the vertex with the c, and then I have my spinor index for this vertex, which is the spinor line, and then I come with the spin Dirac spinner, and that's index A. I guess. So I specify for this Dirac spinner as an incoming particle, I specify the momentum and the spin, the antiparticle as well, and the spin label chooses then which spinner you want. And here I want V, and I think I want V bar S. You know, we had this messy formula yesterday, and there was U's and there was B's and bars and everywhere around, and if you follow through, then it just turns out that this is the U and this is the B bar, and this is a list of roots. Fine. The other way, if the particle comes out, S, you have P, I, P, and then U bar, S, A, and if the antiparticle comes out, I, V, S, A. So that's what the external lines become. So we amputate, take the point away, assign momentum to all of this, and then just write these expressions instead of the propagator. Well, you look also extremely excited. Let's see where I can pick you up, because you're not here yet. Let's maybe being specific is helpful. Let's think about these things. So there's a particle coming in with momentum P and spin S. Now think of this particle. Momentum, spin. And you choose, and the scattering amplitude that we want to compute will be a function of it. Like maybe it scatters better if the spin is parallel to the momentum, or maybe it depends on what this thing does and his momentum and his spin. And we ask what comes out. Can anything come out? I don't know. It comes out with K and R, so momentum K and spin R, and this one with K bar and R bar. And I want to compute this now in quantum field theory, in a specific theory, QED. And so let's try to write down what this means. We have these particles that come in. Let's time flow this way. So coming in, I want from the left, and I really want more space. So this is coming in, and that's supposed to be the electron, say. And this one is coming in. So I'm directing them sort of towards each other, because I think they're going to scatter. Since it's a fermion, a Dirac spinner, I have to give this an orientation. So this is going in, and if a particle goes in, the arrow on that line is this way. If it's an antiparticle, it's kind of going backwards. Do you have a question?
The P bar and the S bar, are they relation to P and S, or are they just another bar to say?
Antiparticle.
So it's not with gamma 0.
Not at all. No. This is a four. The P's are these four vectors for the index, and the bar on the psi is a spinner, and the spinner has spinner index, and so the bar here is psi dagger gamma 0, as you just said yourself. But this bar is. We can also switch notation. In fact, later it is more convenient to call this P1, S1, P2, S2, if it's just those two. Yeah, so the bar is not the Dirac conjugation, it is just the other particle. I don't know, let's leave it for a second. Or shall we change it? We might as well change it now. You like it better? So this is P particle 1, S1, P2, S2, A1, R1, A2, R2. And so this particle that's coming in comes in with momentum P1 and spin S1, and this comes in with 2S2. Out goes a muon and an anti-muon, and they're really different species. I can't just convert one into the other, so there's no contraction between a field for the electron or the muon. So it really is one psi for them and another psi for this one. It's a different one. And since I want to see the difference in the picture, so I decided to draw a double line for the mu field. It's the same type. It's also a Dirac spinner, but it's just a different particle. It's a different mass. Happens to have the same charge, but it's a different thing. So double line. So it looks a bit heavier because it is 200 times heavier than the electron. So that looks very heavy. Now this is what we have, and now we have to somehow connect it. I don't want to draw a dot yet here because I don't really know what's happening. So here we will have to connect these external lines, but I want to do skip ahead. So to fill this with life. If I wanted to write down the amplitude now for this process there, so it is K1, R1, comma, K2, R2, bar, P1, S1, P2, still not gone the top, in, out. Then, I have to draw the diagrams and do all this this junk. Well, it needs what are our options, right? So we can connect this thing with the propagators. They're not the scalar, just the fermion here. So I could just connect the two. And then here. That would be a diagram, a very simple one, but it sets these two momenta equal, and we never had equal momenta in the external states. So there's, what does that mean? They just go fly parallel. We want to scatter them, right? They have at least opposite spatial moment. So that diagram isn't real scattering. We don't want this. I want this connected. This thing really connected. So we will have to have some vertices in there. So in the magic formula, we need an interaction vertex from the exponential. And what vertices do we have in QED? Where do I write this now? Here, vertices, right? I really don't know how to work with these blackboards. If I lift this up, then so vertices start with the 5, 4, y to the 4th degree, and we had this h interaction, which is lambda 4 factorial I 4. And that means we have we have 4 fields, they're all at the same position, and then we can connect to it, so they are all at the same point. Say this is my internal point Z, and there are 4 fields, so there's 4 lines coming out. Every time I bring this down from the exponential, I get these 4 fields at one location, and this factor, lambda 4 factorial, I get a minus I, because the formula said so. That was e to the minus I integral of this thing. So that's the rule. And integrate over the location. In QED, we have an interaction, Hamiltonian, which looks like this. It is the electric charge, right? So this is the coupling, and then we have a psi bar at A slash and a psi. And then of course there's again this minus. So that's the H. In the Feynman rules, it'll be a minus I times this stuff. And then since we might have different particles, different charges, I decided to write a factor of Q. So this is the elementary charge unit, and this is how much of it. Like if it's a quark, it's a third or 2/3 or something. And now how does this look like in terms of lines? So there is a dot. There are 3 fields. So there are 3 fields at the same point, so this will be 3 lines. And then there are different lines. There's a one is a psi bar, so it's a particle and antiparticle. So one is coming in and one is going, like one arrow is in and one is out. Particle, antiparticle. And then the other one is the photon, and the photon we haven't even written down yet. Gets just to distinguish it from the others, wavy line. So this vertex here in QD looks like this. 2 Dirac spinors, particle and antiparticle, and then this photon. And the factor is minus I Q E. And then funny, this slash is a gamma matrix, so there will be a gamma matrix. And the indices of the gamma matrix are mu and A and B. And so this will be a mu index, and one will be an A and one will be a B index, and I don't even know which is which. It's to go, that's the A, and that's the B. And if it's a different field, we just have down line. You want that stuff. Aha, so this is now what we can play with. We can play with these things. We can play with this. Now, throw this in there, as many as you want. Try to use as few as you can to connect all this. But connect it, or I don't know, you can also overshoot and do something complicated, and we will reduce it together. Propose something. Use as many as you like of these things, or for the new one, it looks the same, it's just the double line. And yeah.
So each, or like one of each, I mean,
one of each.
Total, one on the left for the electron positron.
To connect them?
Yeah, to connect them. And then the photon going over into the other diagram, which has the neon and
that was simple. Exactly. So this is the simplest diagram, which just uses 2. And if you have only 2, there's not much you can do. This doesn't look nice. Still doesn't. Yeah. Nice. So that's the diagram. What does it mean? That's the diagram. In the formula for this quantity, so there's this LSZ stuff, and then there's the time ordered exponential of the fields. And in here we have the outcoming, let's call it muon field psi with a double line because it's a double line. And then we have the psi and psi. So we have two incoming electrons, particle and antiparticle, and two outcoming. So this is what this in a schematic way means. The amplitude is you compute this thing, you hash with this ellipse Z. We simplify this by amputation. So we use these rules. And for this in the full theory, in the interactive theory, we go back to the auxiliary fields, the free fields, and insert some factors of e to the minus I integral h into the rotation right there. So every time into the second vertex. Does that make sort of sense? So I'm trying to write down this thing here. The formulas are really big and messy, and the idea of these Feynman rules is to give you sort of this answer by drawing a picture for this and then writing it down, rather than doing all these explicit steps. This is very lengthy. You know, and there's so many indices and everything. But it can be translated into this picture. And so if you figured out how this works, the translation, then we can just start with the picture and write down the expression. So this is what I'm trying to do now, to write down what this is. It has many contributions, and that's one. And that is one of a certain power of the coupling constant, because every of these vertices comes with a factor, and this factor comes with an elementary charge in that one as well. So at order e squared, I get this contribution. And then you can do higher. Since you were so quick, give me one higher, more complicated diagram. Something else that is also, like, use more of them, or the same in a different way, whatever you use.
Internally into more, which I mean, the photon goes again into an internal vertex, which then has I mean.
Oh yeah, so I see what you mean.
I mean, the same one on the left twice.
So here, and then we have another vertex, but then they come back together.
Yeah, exactly.
And then it looks like a circle. And then boom, and this. And now that's not fair because you have an electron going around. You can also have another one with a double line, right? You can also have a muon in there. And then, you know, it gets lengthy. Something I thought was you can just have two next to each other. That's also, it's just as good. It'll be all e to the 4, because we have 1, 2, 3, 4, and here's 1, 2, 3, 4, and every vertex comes with an elementary charge e, and so we have e to the 4 contribution. So you get more and more diagrams, and in order e squared, you have just this. So that's why I can write this equal sign and say, okay, this is the order e squared. And now, I guess I have to write this, right? Now there's a little bit of a, let's say this is the mu part, and this is the mu part. So this, what I really mean is, this vertex is the thing there, minus I Q E gamma mu, and that's not a photon, right? This is just a label, right? This is what goes here, and this is the charge of the electrons, so this is QE, and here I will have minus I Q, the charge of the muon times the limited charge times gamma nu. This is overkill because the Q is just 1 or minus 1, depending on what your sign of the element charge is, but you know. And now I have to write this all together. What is this line giving us? Incoming particle below is this thing. So this will be e to the minus I P1 times Z times U S. And this line here will be this will be an incoming antiparticle. So this will be e to the minus I P V bar S2 S1 P1 P2. So and they are spinors. They have a spinor index. This is a gamma matrix with 2 spinor indices and this. And now this has to all match up with these indices. And this thing is a row, this is a matrix, and this is a column. So that works perfectly if you go this way. And that's a rule. You always have to write down your fermions, yellow, by going against the lines, the fermion lines. So in any of these Feynman diagrams, the fermion lines will always go through. They won't branch. There's never anything that looks like this. That just doesn't work because we don't have that vertex. We have a propagator, this one, so that takes 1 to 1, or we have a here, this thing, which lets the particle go through, but there's no branching. So all the fermion lines will go through, and you can only connect them in the direction of the arrow. So every fermion line will go through the diagram, so will be from an that's not really true. Either it is a loop, then indeed it doesn't end, or if you have an external particle, then it ends there. But you always have these nice lines, nothing branching. And so then this rule makes sense. You always go against the fermion lines to write down your expressions. So this is now, let's say this is fermion line number 1, Roman 1, and I'm going to write it. So I write E to the minus I to V, and that factor goes anywhere, doesn't have any index. Then we have V S2 bar P2. Then comes this thing, minus I E Q E gamma, and then I go on with this E I1 U S1 P. And this thing is now beautiful in terms of spinor product. So this is a row, matrix, column, and works. And so I don't need to bother about explicit indices. All of this is a loop number, or this line number 1. Then we have a second one, and I have to go against the flow, and it's basically a copy, just for the muon. Well, we are on the outgoing side, so let's see if we can get this right. This is a K1 R1, and so K1 R1 for an outgoing particle is E to the I K1. The vertex is called W. W, and outgoing is U bar. R1, K1. Then we have the vertex minus gamma mu e to the I p2 plus q2 w v r2. So this second thing is our second K2. So you're here yet? Here already. So that's there. Now the internal pieces, the internal lines are the propagators, so I'll take them from here. And I do have a photon, but not in my list. Well, this is depressing. Now, what's the photon propagator? I would get rid of something. 5 to the 4th here is boring. Now, the photon is this wavy line in x and y, and this needs not a spinor but a vector index. Say, and then it's dx x minus y, and this is integral d for p pi 4. It's essentially up there. It's minus I eta mu p squared plus I epsilon e to the minus y. So it's minus the metric of the scalar, but then forget the mass. It's photon, doesn't have mass. So I have to write this thing now for this particle there. So times ds mu z minus w. This one doesn't have an orientation. It doesn't. It's symmetric again. Change the order. You replace p by minus p. There's a square. Eta mu is symmetric. So that's good. So I can do whatever I want. This way. It's fine. I just have to write. And now we have all the lines. We have all the vertices, but we haven't yet vertex. Didn't have the vertex rule. There was an integral. You know this formula was an integral. Integrate. You have to integrate over the location of the vertices. So I have to add 2 integrals here. So this is integral over z and w. So that's that. And then there's this awful topic of symmetry factors. There could be a number in front as well. And that is essentially the combinatorics. If we have an exponential of the interaction vertex, and so when you expand, so here it's h, and when you expand this, you get from the expansion of the exponential 1 over n factorial as well. And then there's so many ways of connecting the things. So you have to think about the number. That's boring, and I've thought about the number in this case, and it's 1. So it isn't the most exciting thing, and it's the last lecture of this course. So why do we bother with the number? So it's just this is the answer for this diagram. And now let's try to simplify this just a little bit. So our K1 R1 K 2 R2, P1, S1, P2, S2. In, out. At this order in square is equal to. How do you want to simplify this? Let's pull all the numbers out. So there's a minus I squared. There's a QE. When I wrote the notes, I hated my own notation. This is not vector index, right? This is just the name of the particle, the muon, and that's the electron. It looks awful, but you know, it looks a bit like gamma, right? This is a vector index. Because gamma muons don't have gamma matrices, but they have charge. But that's what it is, right? So this is the charge of the muon. So these are these factors. And then what else do we get? Let's write down all the exponentials first. E for W e to the minus I 1 plus 2 times C. It's coming from there and there, and then the W to the I K1 plus K2 W. Then these spinner things. S2 bar P2 gamma mu U S1 P1. Then the other U bar R1 K1 gamma mu VR2 K2. And now these are dangling a little bit, the mu and u, but they are contracted with the propagator, and I'm going to use this notation now. So the Fourier representation. So P for P is a bad letter, so let's call it Q. It's a dummy, so minus I eta mu Q squared plus I epsilon E, more E. Minus I Q X is Z in our case, and then there's an E to the I Q W. I pulled this apart because the Z joins nicely this thing, and the W joins them if the Q integral wasn't in the way. We pulled this integral, drag and drop here or there. Yes, happy. So this is it, and I promise this is the simplest example, and it's such a mess. Do you know what it means? You pick momenta and spins of the incoming and outgoing particles, and this sits everywhere here, and then out comes an answer telling you the amplitude for this process coming from there to there. Now we can perform the Z integral. So integral over Z. Z is just there and there, produces a delta function. This will be a 2 pi 4 delta P1 plus P2 plus Q. And the W will produce delta for K1 plus K2 also Q. They're all the same signs. And since when we have that, then we can also integrate the Q. All right, so if let's do that. Minus goes away. I squared is a -1. there's a minus I is an I in total, and then we have an E squared and we could EQ mu. This is this. These exponentials are gone. This is about to be done. And then the Q, so there's a Q downstairs, but the Q is equal to minus P1 minus P2 from this. And since this is squared, that doesn't matter. Fine. Since I like plus better than minus is this. So this is the Q of the Q integration. The plus I epsilon I just copy, won't be needed. And now this. So it's VS2 gamma mu U S1 Q1 and U bar R1 K1, and the eta with this gamma is just lowering the index. So I have this protection here. V R2 K2. Done. Not done. We have more two. We have two. We have 2 pi to the 4 twice. 1 goes away, so we have 2 pi to the 4. And then we had these delta functions. I integrated over Q, which removes this delta function, but that's still there. And then the Q is a minus. So it's times delta 4 minus K1 minus, or the other way around, I don't even know, which is nicer. Plus K2 minus P1. There it is. This is your scattering amplitude at this order. And since, so this is what is P1 plus P2 squared? This is a 4 momentum. But just to have an idea what's going on here, let's say our 4 momentum, we are in the center of mass frame. That means the total momentum is 0. So P1 vector plus P2 vector is 0. That defines the center of mass frame. The total momentum is P1 plus P2, and that 0 is center of mass. So then this square, the 4 vector square, which is the energy of particle 1 and particle 2, squared minus the momentum. It's just right, so this is 0. So we have energy 1 plus energy 2 squared. Since they have opposite and equal momenta in the same mass, they also have the same energy. So E1 is really E2. You could simplify it even more. This is 2 times 1. Or we say it's E total squared. I'm not sure if I wrote total, but now I don't like it. I think I want center of mass. So it looks like that. Center of mass. This is the center of mass energy of the system. So that depends on how much you spend on your collider, how much energy you can actually give your particles. One you coming in from the other side, the other from one, the other side. And this energy and this denominator is basically its energy. Now that's sad. Why is it sad? Because it goes down with the energy, right? You spend a lot of money, but it goes down. At least we don't know what the numerator does. They're also pizza case. But instead of now using explicit expressions, which are also awful for these U's and V's, you remember these 4-column things with Pauli matrices and all this. So that's what you would have to use if you wanted to evaluate this now further. And then you can answer questions. A particle with momentum P1 and P2 and spin this and this scatters in this way. Say you don't even know what the spin of your incoming particles is, because you haven't measured it. You just produce your particles and you accelerate them because of their charges, and then they have spin whatever they have. So you'd say you use an unpolarized beam of electrons as incoming particles. Then this is too much, overkill again, because here you need to know what spin is to plug it in. But if you don't have this information, then you don't need the theoretical answer if you don't know this in your experiment, if you have unpolarized electron beam. And the same at the outside. If your detector, which detects the muons, doesn't know what the spin is, it just counts them. Maybe their energy, so the momenta, it detects, but not the spin, then we don't need this information either. So what we could do is simplify this and say we don't want this information. What does that mean? You would basically average the incoming spins. And since you collect everything in the on the outside, outgoing side, you sum over the spins. You sum over the spins of the muons, you sum over this R's, and you average over the incoming spins. Does that sound good? Then if you do that, we don't have to have these explicit expressions. We will get away with just using the completeness relation. It makes sense, right? These components there, these specific spinners with a specific spin. This tells you, okay, wherever it's pointing, and you have a specific form. But if you don't care about this information, and then you sum over everything, and then it's just the completeness, doesn't it feel like completeness? If you have a vector and you can now project it on X and project it on Y. But if you don't care, you add the projections again, then you have back your vector. Right? So if you average over the incoming and sum over the outgoing spins, then we don't need explicit expressions, and that's why we want to look at it. The question is now, how are we going to sum and average? Like, do I just write a summation here, sum there? Do I add this amplitude plus the one with the other S's? And that's now this is the question, what you have. Do you have a coherent superposition of your spins? You know, if you have a spin up and a spin down with a specific sign in between, say plus, spin up plus spin down, what is that? What do you remember? What is that? Normal spin 1/2 up plus down. I don't even remember. It's probably it's probably spin in the X direction, right? It wasn't it like something like this, if you spin to the right, there's 1/√2 up plus down or something like this. So if you add the states, spin up and down, then you just get you get a different state. This is a quantum mechanical superposition. And they can interfere, and they interfere to something new. That's different from saying, I don't know what my spin is, and I want the probability of the two different options added up. So I don't want to add the states, I want to add the probabilities. Does that make sense? If you know, you do Stern-Gerlach or something like this, and you send these spins in, and then there's a question whether you send in the superposition of a spin up and down, which is a spin in the X direction, or if you send it either up or down, but you don't know which it is. behaves differently, right? So what is this now? What we have to do here is, because we have an unpolarized beam, it doesn't mean up and down is quantum mechanically superposed, but it's just that we add the probabilities. So this is the probability amplitude. This thing is called the scattering amplitude. So we don't add amplitudes, we add probabilities. So next topic is, how do we get from the amplitude to the probability, the scattering probability, which we then sum, and then we have an answer. And now it's 10:15, and writing down, yeah, I will only be able to sketch it, but it's fine, right? It's Friday, it's not relevant for your exams, so why don't we just sketch it? It is not sketched in the lecture notes if you happen to care. Then you see the derivation. It's also not really the fundamental task for quantum physics. It's more for particle physics. And you have a particle physics course, I heard, and there you probably know. So it's 8.2 cross section. Have you heard the word cross section in this context of scattering? You have heard it. Can you tell me what it is? Because it's everywhere. You need to know, you don't need to know the details, you just need to know, like, what's the idea? What's cross section in?
I don't have the course at the moment, but remembering back from bachelor,
Yes.
I think it's something like at what probability we measure, or what probability at a certain angle the scattering has, or the.
Yeah, roughly right, roughly like this. You're talking already about the differential cross section because you think about the direction in which stuff goes. If I say in everyday life, the word cross section, isn't it? You take something and you cut it, and then you look at it and you see, oh, the cross section is circular or something, right?
How big it appears to.
How big it appears, right? And you can hold it in this way or in this way, and then it's a different, like the shadow it casts, essentially. It literally is the cross section of something. So if there's an obstacle, now this is not a muon or neither an electron, it's just this owl there, and it's a rigid body. And now you shine with light or something, and then it casts a shadow. So depending on its cross section, like you cut it, you see, I don't know, I get this is a stupid owl. I don't know, it goes up down there. So I guess, you know, this is there's a cross section area. And this is called sigma. So sigma is an area. It really is just meter squared or millimeter squared, something. It is the size, the area of the shadow it casts when you look from a certain direction. And so let's say we have this thing there and we come and hit it with a bunch of particles, our beam, and they're flying there. This is what casts the shadow, right? And so I assume I have a homogeneous density in there. So my particle density n is particle per volume, particle density, and I want to know how many of them will be deflected. So if they hit this thing, then they're gonna go. If they don't hit the thing, they're just gonna fly straight. And so how many hit this thing? If I take a box that happens to have this cross section here, so if this, this is a cylinder that is just made, all of them inside just gonna be blocked. Say I pick a volume which has the exact cross section. So this cross section here is sigma, and it has some length. And so if we go with the length that I want to pick is the distance they fly in a certain amount of time. So here I'm choosing velocity times time. We wait for the time t, and then they fly because they have a velocity v, the distance v times t. And in that time t, these many guys will be deflected. I mean, not exactly those in here because they have still a little bit to go, but this is homogeneous and they're everywhere. And in this time t, everything that's inside will be deflected. So the number of particles, number of deflected particles is equal to what's inside the box. So let's call this number n. N is everything's in the box, and what's in the box? It's the density times the volume, and the volume is the length times the cross section. Ooh, there it is. So the number of particles that are deflected by such a beam is given by the density times the volume. And we're now solving this for sigma. Sigma is n divided by, that's not so hard. This is probably the best computation of today. So the size of your obstacle, the sigma, the cross section, is given by the scattering rate divided. This is the scattering. I wrote the t from the bottom to the top because n divided by t is the number of deflected particles by the time that I wait. So it's the scattering rate, how much scatters in the time. So per unit time. This is and n times v, it's like density times velocity. This is the flux. Incoming flux, of course, incoming. It's just incoming. But I write it down. Flux. No, flux. Flux is number of particles per area per second. Remember in electrodynamics, the current is density times velocity. And so this is basically this density times velocity. This is the current. And that is now charge per area per time. So this is not charge per area and time, this is just number per area and time. So the observable that experimental physicists like is this cross section. And the cross section is literally the size of the obstacle. If you have a classical picture, like if you do classical scattering, then you have something solid, and then it is what the shadow cast and stuff. If it's quantum mechanics, it's all fuzzy, and it doesn't have a specific size. Then it's sort of the effective size of the obstacle, right? If you have an electron here and a positron there, and then they collide and they do something. So the electron is an obstacle for the positron. And the sigma that we are computing is sort of the size of this obstacle. So the cross section is not literally a probability or something. It's an area. And I think it's really good to think about it as this shadow. And then quantum mechanically, you get the fuzziness. It's like the effective area, size of the obstacle. And the differential cross section that you were talking about, this is when you look at where it deflects. So I can, instead of just take the whole thing, let me pick all the spots of my potato here, which deflect in precisely this direction. It's going to be tough. I don't even know. Here there should be someone else, and maybe that's it. So I have to look at all the different places that scatter my particle in this direction. And the sum of these parts, like that part of this big area, this sub area essentially, that deflects in a certain direction, that's called then the differential cross section. How much area of this total cross section deflects in a certain direction? This is all continuous, of course, and you have a derivative. The differential cross section is basically d sigma by d, and then the angle in which direction it goes, omega. Now I have to see what I will feed you. That's too much. The steps that need to be done now is to use these words to figure out what is the sigma in terms of our scattering amplitude there. So we need to convert the scattering amplitude into a scattering rate and divide by flux. And then when we've done that, then it's called sigma. And so the first thing we need to do from the scattering amplitude to the scattering probability how do you go from amplitude to probability? Squared. Exactly. So the probability P, what's that? Is the square of it. So it's K1. Let's talk about this in general. So K, all the K's, and then P's, and then squared. And that's a probability only if, well, you have to make sure something works, right? Like, I don't know, remember quantum mechanics. When is just squaring enough? Exactly. We have to have this properly normalized. So these states, these two states have to be normalized. Then you have this state, and then you project it on it, and then you get immediately the probability. But these things aren't really normalized. They are just awfully normalized. First of all, they are normalized in this relativistic norm with some energy factors. And then they're not even normalizable because they are continuous momentum eigenstates. So we have to write explicitly K1, so K1, K1, 1, 1. Now this is turned over to 1, so this is the probability. And as I just said, none of these norms or the scalar product here are super well defined. Because this is delta of 0, and this one, what's that? Here, we want to square it, so we have a delta function, and squares of delta function are never good. So whatever you have, delta function of some argument, say x, that's okay. But now you square it, so you have delta of x times delta of x, same x. But since this is only non-zero, if the x is 0, you might as well set this x to 0. This sets x to 0, so this will be this. And delta of 0 is infinity. And this will happen here in the numerator because of this squaring. And it will be here because they're delta of P1 minus P1. So you have always everywhere these things. And in the quotient, however, you can work through all the details and see that these infinities cancel. How you do this, how you cancel infinities, it's not just infinity, infinity, and then cancel, because you don't know whether this infinity happens to be twice that. So you have to be a little bit more sophisticated. And the idea was delta of 0 is integral. So if you have this thing, this is a delta function of p. And if you have a 0, it's basically when there's a 0. So e to the 0 is nothing. So this delta of 0 is the integral over all of space. And if it's a 4-dimensional one, it's really all of space-time. And then there's a factor of 2 pi to the 4. But you know. So this is the entire volume of your space and time. It's infinity. But we have kind of regulated it by not writing infinity, but saying the entire volume, the entire time of the universe, from whenever it was created to whenever it, like asymptotic times, everything infinity, but in written in terms of these letters. And then you have v's and t's everywhere, and you can cancel them, and then comes out. I would have written it down, but there's no time. The t that sits in here will actually give us the rate. Because I want the rate, I want divided by t. This is the probability of something happening, divided by t, so that t is already very nice. And then you have to integrate over all your options, where the particles go, so over these p's here. And so I guess at the end of the day, you end up with this formula. Everything that is okay to square, like this, which is our amplitude without the energy momentum conservation delta function, without this. Everything here is called m. And that is called, I don't know, this is the worst name. I don't even want to say it. But you will find it in the book. So it's the invariant matrix element. In other books you find it's the Feynman amplitude, which is a bit nicer. Feynman M. It's called that because it's what the Feynman rules give you. The version of the Feynman rules. But this is the M. So M is essentially our scattering amplitude. But stripped off this thing, and we stripped it off because we can square it. So we squared this by hand, and that'll be in there. So the formula after yaka 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 is the sigma is equal to, and that's wrong, integral yeah, let's say we still produce L particles on the outside, on the outgoing side. Then you have EKJ, all three, 2 pi, 2 EKJ, the energy of this particle. Now here comes the squared. And then this is the flux part, particle 1. I call it E1, E2. So this is the energy of the electron and of the positron, which is the same. Then we have the relative velocity, and then it's just 1 these factors then. Q1 is Q1. God damn it. Q1 minus Q2 minus KL. So this is now the way from the amplitude to the observable, the cross section. And people measure this. Then we measure the differential one. The differential one you get if you don't integrate. Just forget about this integral here. Don't perform the integration. Just like that. And it is essentially the scattering rate divided by the flux. So this thing I didn't show is written down. And now, the rest I can't show either. Oh, this is so sad. If so this is very sad. If we did this now for our process here, the electron positron into mu minus mu plus, then that's very nice. So how many, let's just count the integrations, right? We have two particles out on the outgoing side. That's how many integrations over k? How many k? How many integrals? 2, but then there are 3 dimensions, so it's 6. Let's count 6. And we have a delta function. And this is only 2 particles. How many delta function worth? Four. Because it doesn't matter how much is in there, it is always just these 4. So we have 6 integrations minus the 4 from the delta function. So we can actually explicitly do 4 and are left with 2 that we can't do. And these 2 integrals are exactly this, about the angles away from the beam and to the side. So you can blah 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 simplify this more, and you get, okay, let's write it. For the 2 to 2 scattering, when you do these 4 integrations, you are left with this omega for m. The center of mass momentum on the outgoing side, the center of mass momentum on the incoming side, and divided by, we figured this out, the E center of mass squared. So this is now this formula. And I wanted to, I don't know what I was thinking, I can squeeze into 90 minutes, but I wasn't in my, I don't know, judgment bad. We want to square this thing now. That makes it bigger again. Then we want to sum and average over the spins. That makes it smaller again. In fact, it makes it quite neat. And then you can write this thing down, and the answer is this. This is the sigma 2 to 2. So this is the sigma E minus E plus scattered to E minus plus. And here it starts at 2 masses of the muon. If your center of mass energy, if the energy to provide isn't equal to twice the muon mass, you're not going to produce any muons, let alone 2. Yeah? But if you can produce them, so these 2 electrons annihilate into just pure energy, and that's this energy. And if that energy is large enough to produce 2 muons, you will. And if you have more energy, then it produces more of them. So then, like the size of the obstacle is bigger, so you have more of the scattering happening. And then, if the energy is large, then it falls down. Then basically you miss it. You just run right through it or so. So then it goes down. So this is the picture of it. And now, why was this an important process experimentally? If there was another particle, like the tau one or the charm quark, this is how the charm quark was discovered. So there was suddenly another jump, right? I guess like this curve again, but starting somewhere else, and then you add the two. I mean, you can also, if you know what you're measuring, then you have another picture for the other one. But so every time there's a new particle that can be produced here, particle with this antiparticle friend, then you'll see this in the cross section. So this is how all these new particles have been discovered. And even if you have now a quark, anti-quark produced, they have also a certain mass. So at some mass, they'll come in. From the height, you can even tell how many quarks are there of that mass. And there was this funny number 3. It looked like that there are 3 tron quarks. And that 3 is what? The color. You have up and down and bottom and top and strong, but they have all different masses, so they come at different energies here. But there's like a triple. There's 3 times as many as you would think from the neon. And this was on the color. So this is an experiment where you show that there are 3 colors, and that's not 4. There's not an undiscovered 4th color. Because if the quark is here with a certain mass, you would have produced it. And if it's just 4th color, then you would have seen a higher bump. But you have, so it's just there's 3 colors. It's very nice. I'm not going to compute anything more, but I will show you a picture somehow. This should come, or maybe I can. Do you know what the magnetic moment? You know, the electron has a spin. And the spin is a rotating charge. It's a charge, it's rotating charge. Rotating charges are compass needles, like little magnets, and they interact with another magnet. Magnets interact with magnets, and then the compass turns in the electromagnetic field of the Earth, and so your electron feels an electric or magnetic field, and there's a relation between how much it spins and how much its magnetic moment is. And the Dirac equation predicts a certain proportionality, like a nice simple ratio. This zero magnetic ratio is 2, whatever, in units of Bohr magneton. This is just, there's the number 2. Experimentally though, you find that this ratio of this magnetic moment to the spin isn't 2, but 2 comma blah 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 plus, I guess, plus 0.1%. Let's write it like this. So it's too big. Oopsie. And the number, I wanted to show you the numbers. I don't know why it doesn't show, but that's too sad now. Again, this is a sad ending. You know why? There's a table that can actually transport. Boom! Lights off. 1 second. Oh, this is too small. So if it's close to 2, so what people define is G minus 2, and then for good measure divide by 2, and then they call this the anomalous magnetic moment of the electron. So the AE is what's recorded here, and that's a paper, and it reports on an experimental value there. So if you subtract the two, this is already very small. 10 to the minus 12. So this is also dumb. I mean, what this number is really 0.001. 0.001 is my 0.1%. So that's that. So it's minus 12 by that. But just look at the number 1, 1, 5, 9, 6, 5, 2. They have measured so many digits, and this is the uncertainty. And now you compute in a fashion like this. What you have to compute is the Feynman diagrams that have the interaction of your electron with the photon. So basically, really just this is a 3-point function. And then you get a number, and you get this number 1, 1, 5, 9, 6, 5, 2, 1, 8. Oops, but it's so close. It's just freaking close. And why is there two different numbers for the theory? Because the theory, all this renormalization business, it needs an input value. You'd have to have something measured, which you insert into this theoretical computation, and then it comes out this prediction. You can't just predict this. You have to input something. And what's input is the fine structure constant up there, this 1 over 137, and that is an experimental error too. And if you use one or the other, you get this or this. So it's just extremely close. It's just so close. Just imagine, right? You had to explain this deviation, and then somebody presents this quantum electrodynamics, and you compute it. What they have computed now is these diagrams here. I wanted to show you the diagrams. This is the first correction. So when you have this, what else where can you put more of these vertices? Well, I guess you can, that's the line that goes through, and that's the external one here, and just put an arrow. This is the first diagram at this order. It's the second order because of 1, 2, and there's only this diagram. If you go to the next order, then you have this. At fourth order, there are 7 diagrams, of which only 5 are shown because others are just reflections. So I want to point out the 7 diagrams in fourth order. Then you go 6th order. 6th order, you have these diagrams, and you have 72 diagrams. Like if you decide to work on this, it's an order more than that. Like if you thought that was exhausting, then you wouldn't even start this. Every new order is at least an order of magnitude more work. This is negligible in terms of work when you go here. And then, okay, 6 is not enough. Now you go 8. And you have these diagrams, 891 diagrams. And this is already with all the tricks of amputating and all this stuff. And then they went up to the 10th order, and then these are these diagrams, and then guess how many there? 12,672. Why is it doesn't show here? My point is, you get a number with so many correct digits. It isn't entirely wrong, although there are sketchy pieces in the derivation and all of this. But people can manage these infinities and extract fantastic numbers. So, and this is the point where this course actually ends. I know this was sketchy. You're not going to be asked to do this in the exam. I hope it connected it to something that you'll now see in other courses, and so you know what a cross section is and how to get there in principle. I have not forgotten that I promised a mock exam. I'm still working on this. I don't know when you'll write this, whether it will come and you write it here, or you'll just look at it at home. And I have to do it quickly, so that it comes, but it's going to come. Yeah. Questions? Comments?
To ask how to get rid of the epsilon.
Set it to 0. At the end, you're supposed to set it to 0. It was just regulating it. And since this denominator is the energy, the center plus energy and your collider produces energy, the denominator is never zero. So it was only important when there was a pole to go around the pole. Here, it can be set to zero. Yeah, and that happens also in all these other diagrams that I do at the end. All right. Well, thank you for this course and staying here till the very end. It was a joy, yes.